Yes, guys. Now today I have to talk about quadrant area under the curves, okay, or quadrants. Quadrants means area of a curve under the or area under the curves, okay. In this case, today we are discussing about polar equations. When the curves are in polar forms, then what are the areas, okay? So that is the point of today. Let me first describe that what are the polar coordinates we already described, okay, in case of curve tracing, in case of polar coordinates, and then Cartesian coordinates, parametric equations, etc. That we have discussed in detail, okay. But today I'll just prove that what is the area under the polar curve, okay. That is the first expression I'll just discuss about that. If r equal to f theta, where f theta is a function of theta, is a continuous function of theta, okay, and where radii or is lying between radii r equal to theta equal to alpha to theta equal to beta, okay. These are the two values, okay, in which under which this this curve is lying, okay, the arc of the curve, and the AB arc of the curve we will take, and we will find out that what is the area of this curve, okay, or of the arc AB under the angles, these angles, okay. That will describe that how to find out area under the curve, under the polar curve, okay. So that is the point. First I'll describe that how to find out areas of a polar curve, alright, or a curve in if it is expressed in polar form. So that is the point. Then I'll take these questions, which are 17 questions I've taken. Okay, a number of questions I've taken here because most of the queries of the students, because this topic is not clear most of the students. So that's why I've taken a number of questions, so that topic can be clear to the students, or they can have clarification regarding this topic, this topic. Okay, so let me take by polar curves. Today I'm taking polar equations, okay, quadrature or area under curves or area of curves by polar equations. So let me take that what is the polar equations or area of a polar equation. Let me define that, okay. If r is equal to f theta, if r equal to f theta with the function, continuous function, with a continuous function, with a continuous function of theta, okay, and between the radii, okay, r is equal to, if I take r equal to alpha to r equal to beta, if I take, okay, those are the points here, or theta equal to alpha, theta equal to beta, okay, and theta is in the domain where a function of theta between the range, let me take range of the theta between the range, between the range alpha to beta, okay, where angle theta is equal to alpha to theta equal to beta. This is the beta. This is the range of the angle theta equal to alpha to theta equal to beta. So between these two range, we have to find out what is the area of this curve, this polar equation r equal to f theta we have described, where f theta with a continuous function of theta between the range or in the range, between the range or in the range, let me take in the range, okay, alpha beta, where theta equal alpha to theta equal to beta. So this area we have to find out. So that is the point of today's discussion, okay. So theta equal alpha to theta equal to beta, and this area is given by theta in the domain, and the radii vectors, where this is between the radii vectors, okay. The range of theta is this, and between these two radii vectors, between the radii vectors, I have to talk about between the radii or radius vectors, between the radius vectors this theta equal to this. Okay, or between the radius vectors r where theta is alpha and r where theta equal to beta. Theta equal to beta. So this we have taken here, and this is given by this area is given by. We have to prove this. This area is given by alpha to beta. This is half r square 1.2 r square d theta. This we have to prove here that this is the area equation. Of this polar coordinates or polar equation r equal to f theta. We have with the continuous function of theta in the range alpha beta, or in the under the radii vectors for which theta equal to alpha to theta equal to beta. Okay, is given by this area equal to, or this area is equal to 1.2 alpha to beta r square d theta. So this we have to prove here. Okay, so that is the main point here, where here alpha, or if I take alpha to beta, or if I take a to b, doesn't matter, where alpha is smaller than beta. Here I have to take where alpha is naturally smaller than beta. Beta is larger. If I take, let me take a curve here, or let OX be a, OX is the initial line. This is the OX. Okay, let me find the solution of this. Let me prove this, that area is this. Solution. Let OX be the initial line of this, polar coordinates here. OX is the initial line and O the pole, and O be the pole and O be the pole. Let me take here O B. Let me take here OB. This is B capital, OB point. And if I take from this B point an arc like this, okay, arc like this, if I take, and let this OA, this is the A point here. So this angle is alpha here, and this total is beta. So radius vector for this OA radius vector, we have taken the angle alpha, theta is alpha here for A, and for OB, theta is beta. This we have taken here. Now if I consider, let me take a smaller element here. Okay, and this is the P point. Let me take, this is P point. Let me have this point, and this up to this point P, it is theta angle. Okay, and this is delta theta. So we can say that angle O or POX is theta angle. Okay, and angle POQ is delta theta, because R coordinates we have taken, Q coordinates we have taken R delta theta, R plus delta R, and theta plus delta theta, and for P we have taken R and theta. Theta is the vectorial angle for P and R radius vector. Okay, so this is what we have taken R, and this is R plus delta R. For Q, position vector OQ is R plus delta R, and for P, position vector OP is R, and angle theta, and this is delta theta, so R plus delta theta, or theta plus delta theta is a radius is the vectorial angle for Q at the point. Now if I draw a perpendicular from P on, let me take OQ, or let me take this meet at PQR, let me take here R, and from Q if I draw perpendicular to OP produced at S, let me take, this is the S point here, which means that S. So we have to just prove that OPQ area is larger than OPR area and is smaller than OQS or OQS. We will prove that this area, and if I take this area, if I take area OPQ, this area OPQ as S plus delta S and ORS, OPRS S. So S plus delta S minus S will be ds or delta S. Okay, the delta S we have to find out. We have to divide that area. In this case, these two areas we have to find out. Okay, now let me take what are these two areas, or what are these two values here, and what is this distance, what is this area. OPR is what, and OSQ is what. Okay, so by sectorial angle, we know that by sectoral area or area of a sector we know about. So solution, let me find out. We are finding out solution. Initial line and theta be the pole. Okay. Further, let OP is equal to R and OQ is equal to R plus delta R, and angle and vectorial angles, let me take, and vectorial angles for P and Q are angle POX is equal to theta, okay, and angle QOX angle equal to theta plus delta theta. This implies that angle QOP, angle QOP is equal to delta theta. Simple. Okay, so this is some description. So we draw perpendicular PR to OQ and QS to OP, which meets OP produced at S. Okay, so QS we have drawn perpendicular, and this we have drawn perpendicular. So what are these three areas we will compare? What is the area? OPR, area OPQ, and area OQS. These three areas we will take. But we have to find out what is the area OPQ, because this is the smaller element we have taken. This is smaller element we have taken up to this. So area, let me take area of OPQ. Okay, is, let this area of OPQ is equal to, okay, is smaller than or is described as, okay, let me describe it. Area OPQ, we have taken this as, okay, let me take this ds, or if I take this area, okay, no, we have to find out this area, but before that let me take area of OPQ, but before that let me take, what are these two areas, or let me take, further let area of OPA, area OPA is equal to S, and area OP sorry, OQA equal to S plus delta S. Let me take. This implies that area OPQ, area OPQ is equal to this area minus this area is equal to area OQA minus area OPA. OQA minus area OPA, this means the middle area OPQ, which is equal to ds here, S plus S, or let me write S plus delta S minus S, let me delta S only. This is S plus delta S minus S equal to delta S. Now this area delta S, which is OPQ area, which we have to compare. Okay, so this is delta S. What is area? This OPQ area. OPQ area is delta S. We have taken. Now let me further solve it. That what is the area delta S? Now area sectoral area. This is sectoral area. Sectoral area, from sector we know about. From sectoral area OPR. OPR is R into delta 1.2 R. This is 1.2 R square, because this is the base R, into 1.2 into delta theta. Because delta theta is this angle, or 1.2 R square delta theta. And area OPR, OPQ, this we are taking OPR, and area OQS. Area OQS is equal to 1.2 R plus delta R. This is the whole square into delta theta. Okay, because this angle is delta theta, but this total width is OS. OS is equal to OQ. OQ is R per delta, so R per delta R square delta R. So now we can compare. But as we see, but area, this one which is OP, but area OPR is smaller than area OPQ. Area OPQ is smaller than this area, last area. This is OQS. Okay, so this is the comparison between three areas. What areas? OPR, OPQ, and OQS. OQS is larger than OPQ, and OPQ is larger than OPR. Simple. This we have written down here. What is OPR? This is 1.2 R square delta theta. Is smaller than. This is DS. We just calculated, or delta S or DS. Let me take. This is delta S. Let me take. This is delta S here, which we found out. Area OPQ, which I found out as delta S, is smaller than half R plus delta R whole square into delta theta. Is smaller than this. Okay, at delta theta tends to 0, or when delta theta tends to 0, delta R also tends to 0. Okay, so delta theta tends to 0 implies that delta R tends to 0. From this, it means delta S upon delta theta. Delta S upon delta theta. Okay, when in the limiting position, limit delta theta tends to 0, is equal to 1.2 R square only. Okay, or ds upon d theta is equal to 1.2 r square, because this is line dr, delta r is 0 and delta theta can be taken to the base of this, so delta s upon delta theta is equal to 1.2 r square. For this line between 1.2 r square 1.2 r square, so you can take ds upon d theta equal to 1.2 r square, or this implies that ds is equal to 1.2 r square into d theta. Now putting the limits here, so between the limits theta equal to alpha to theta equal to beta, so what is the area therefore finally? Therefore, applying the limits here, this area, therefore applying the limits 1.2 r square, this is alpha, theta equal to theta equal to beta into d theta is equal to, this is limit alpha to beta is ds, and this is s here. If I put limits alpha to beta, so this will be area, and s area is OA P, area OA BP have taken now. We have to apply this from A to alpha to beta. This is nothing but area OAB. Area OAB. Okay, because this is equal to area S when theta equal to beta minus area S when theta equal to alpha. So lower limit and upper limit we have to put first. This is equal to OAB only, because this area below alpha, because angle this we are not considering. We are considering area only A to B, to between these two limits. So this is the area ds equal to, or area under the curve AB, which is arc hole length. AB is the arc hole length of the arc under which we have to find out the area. So this area is given by 1.2 r square. Yes, 1.2 r square d theta. 1.2 r square d theta. This we have proved from this. This is the basic formula for curve. For the area under the curve in case of polar coordinates, or in case of polar equations. So polar equations are given, and we will put this formula again and again. So we have to just understand that how this area is obtained. This is very important point. This is applied for all these questions. We will apply. Now let me take the questions one by one. This is the basic formula for area under polar curves or polar equations. Okay, so this formula we apply, and this is for polar equations, area under the polar equations or polar curves. Okay, so this formula we have to apply, and this I have proved that how to find out this area of an arc AB, for which position vector r is given, vectorial angle or radius vector and the vectorial angle both are given. In that situation we find out area. Okay, so now let me take questions one by one. Now in this case, question number 1, let me take. Question number 1, it says, find the area of the curve R square equal to A square cos 2 theta. Okay, let me take. Here, question number 1, the curve here, the polar curve, polar equation. The curve or polar equations is R square equal to A square into cos 2 theta. Now if I trace this curve first, and after that let me find out the area. If I put solution, this we have done in case of tracing of the curve in case of polar equations. This we did, but let me again do it. So putting this equation here, if I put theta equal to minus theta, okay, then this will not change. Even if I put r equal to minus r, then also this equation will not change. Putting theta equal to minus theta and r equal to minus r, the curve does not change. So this curve is symmetric to this curve is symmetric to the initial line, initial line, and its curve is symmetric to the initial line and the line at theta equal to pi by 2 to the initial line, and the line at theta equal to pi by 2 to the initial line. Okay, that is there. So this is initial line and this. So first let me, I'm going to draw this, but before that let me find some points here. That what is the position of the curve? This is x axis, initial line. I'll take O, origin here. This is theta at pi by 2. This line is, or this is y axis, but we have to take the initial line, etc. Now let me put r equal to 0 in the beginning. Putting r equal to 0 in first, this is the first equation here. In first, we get, what do we get here? This is cos theta or cos 2 theta equal to 0, or 0 cos pi by 2. This is, therefore 2 theta is equal to plus minus pi by 2. Because for minus pi by 2 also cos is 0, or plus pi by 2 also it is 0. Therefore theta equal to plus pi by 2 and pi by 4 and minus pi by 4. The curve is lying between pi by 4 to minus pi by 4, and other points are also there. Okay, so 3 pi by 2, so 3 pi by 4 and 4 and 3 minus 3 pi by 4. That is also the point that will lie. Okay, it's lie between those 2 points. But where this curve meets the initial line, where the curve, if I put theta equal to 0, then putting theta equal to 0, we get r square equal to a square only. Why? Because cos 0 is 1, or r is equal to plus minus a here. That means r equal to plus a and r equal to minus a. So here let me take, this is the point r equal to, but theta is 0, r equal to plus a. This is a and 0. Here it is, let me take minus a and 0. The initial line is being met by the curve at the initial line, this point, and it's passing through the origin also. So this is the curve, let me take, passing through the pole and meets the initial line at these 2 points, minus a and plus a, and lying between the angle pi by 4, this theta equal to plus pi by 4, and this is theta equal to minus pi by 4. Theta equal to minus pi by 4. This angle is lying between, and here this is also lying between theta equal to plus pi minus pi by 4 and those 2 points. Okay, so this is area we have to find out. We have to find out find the area of the curve this. So let me first find this area. So here it is d theta. Okay, and also this is not x-axis type. I'm sorry. Here we have to take this kind of elementary strip. Okay, so this is P point, this is Q point, and this is delta theta here. Now in this case, we find out what is the area. So twice of this area, or area under the, why twice? Because this area is also the loop. This loop is also included. twice of this area minus pi by 4 to plus pi by 4 angle. So area is equal to this. Let me take O. O is point here. This capital A. Let me take point B here. Twice of area of this loop, area of the loop of this is twice, but again we will do twice of this, so that will give us total area. But first let me find out area of this. Area of the complete wave, or required area. Required area of the curve. Required area of the curve is equal to twice into area OAB. So this is equal to twice limits minus pi by 4 to plus pi by 4. Or if I not to put twice, because twice is for this, or let me find not twice. If I find upper area, then 0 to pi by 4 limits. If I put 0 to pi by 4, then it is twice. But if it is only minus pi by 4 to plus pi by 4, then it's single only. The total, because this total area is covered. This is 1.2 r square. This is 1.2. The formula, same formula, we will substitute here for polar coordinates here. This area is 1.2 minus pi by 4 to, in case of alpha we have minus pi by 4. Case of this is, but it's not twice now. But if I take twice into area OAB, then limits are 0 to pi by 4. This is the point. But here I am taking minus pi by 4 to plus pi by 4. It can be written as twice into 1.2. This is 0 to pi by 4. This is from property 4th, I think, of definite integrals. This is r square into d theta. So twice 2 to cancel out now. 2 to cancel out. This is 0 to pi by 4 r square d theta. Now let me substitute the value of r square. Here r square is a square cos 2 theta. So let me substitute that. So these are the two loops. One loop we are calculating, but if I make twice of that finally, whatever answer of this is obtained, or that I make twice of that, and that will give the total area of this curve. Okay, finally what is the total area? So let me put that value. This is equal to this value, okay, 0 to pi by 4, r square is this a square into cos 2 theta, okay, into d theta. Now if I put the limits 2 theta, let me put 2 theta is equal to 5. That means